At the end of this section, you should be able to find the derivative of a composite function using the chain rule. Find the derivative of a function using the general power rule. Simplify the derivative of a function using algebra. Find the derivative of a trigonometric function using the chain rule. Differentiate natural exponential function. Find the derivative of functions involving the natural logarithmic function. Differentiate exponential function that have bases other than e. We have yet to discuss one of the most powerful differentiation rules, so-called the chain rule. This rule deals with the composite functions and adds a surprising versatility to the rules discussed in the two previous sections. Compare the function below. Those on the left can be differentiated without the chain rule, and those on the right are best differentiated with the chain rule. Now I show you the right side function. Those can be written in composite function. Look at the first one. We can let our inner function of this function equal to x squared plus 1. Inner function is gx function, and the outer function fx equal to radical x. And for the composite function f gx is equal to x squared plus 1. So that is why we say this radical x squared plus 1 is a composite function and is the base differentiated via the chain rule. Basically, the chain rule states that if y changes dy du times as fast as u, and u changes du dx times as fast as x, then y changes dy du times du dx times as fast as x. If y equal to fu is a differentiable function of u, and u equal to gx is an inner function, is a differentiable function of x, then y equal to f gx is a differentiable function of x, and dy dx equal to dy du times du dx. When applying the chain rule, it is helpful to think of the composite function f gx as having two parts, an inner part and an outer part. So look at the composite function y equal to f gx. The gx is inner function, or u, and the f is outer function. The derivative of y equal to fu is the derivative of the outer function at the inner function u times the derivative of the inner function. So now look at this example. Look at here, the ABCD. The function here, they are composite function, y equal to f gx. Now, look at how we split the inner function. For the A, we can say x plus 1 is inner function. So, y can be written as function of u. Y equal to 1 over u. The function y equal to u is a function of x. Power to the n is one of the most common types of composite functions. The rule for differentiating such functions is called the general power rule, and it is a special case of the chain rule. You should recognize in which situation we should use the general power rule. Recognize this form. When the function of x has power, look at this theorem. If y equal to ux power to the n, where u is the differentiable function of x and n is the rational number, then dy dx equal to n times ux power to the n minus 1 times du dx. Look at this example. Find the derivative of fx equal to 3x minus 2x squared power 3. This is a composite function. And why we use the general power rule? Because of 3x minus 2x squared is a quadratic function. And this quadratic function has power cube. So that's why we use the general power rule. And now I show you why this is a composite function. I can let the inner function gx function equal to 3x minus 2x squared, and my outer function fx equal to x cubed. So my f gx is equal to 3x minus 2x squared power cubed. So from here, the proof here, the inner function is 3x minus 2x squared, or equal to u. So our function can be written as function of u. So equal to u cubed. And since this quadratic function has power cube, so we use the general power rule. So this is a general power rule. We move the n to in front, and u power to the n minus 1, 3 minus 1, 2, times u prime. Differentiate the u with respect to x. To differentiate the u, this is a in the different form. We have covered this part. We straight away to differentiate. So we have 3 minus 4x. So this is the answer. The next 3 examples illustrate some techniques for simplifying the row derivative of functions involving product, quotient, and composite. Look at this example. Find the derivative of fx equal to x squared times radical 1 minus x squared. This function is in product form. We write the original function, and after that convert the radical 1 minus x squared to the power rule form. And as I say, this function is in product form, so we use product rule. So this is a product rule. We differentiate the second function times first function plus we differentiate the first function times the second function. And the next, we use general power rule for this part. Look at this part, I repeat, because 1 minus x squared is the quadratic function, and this quadratic function has power to the half. So we use general power rule. So you refer back the formula of general power rule and move to in front. U power to the n minus 1 times u prime. Then plus differentiate the x squared. So we just use power rule. So we have 2x here. Then we simplify. And then we factorize. And we simplify. And lastly, this is the answer. Look at this example. Fx equal to x over cube root of x squared plus 4. So the function is a rational function. So the main rule is quotient rule because it's rational function. So we use quotient rule. The numerator is a function of x and the denominator is also a function of x. So we use quotient rule. So now the next step, rewrite the denominator to be the power rule form. And we apply the quotient rule. For the quotient rule, we differentiate the first function, which is 1, times the second function, minus we differentiate the second function times the first function. Be careful with the second function. Look at the second function. It's a quadratic function, has power 1/3. So we use general power rule. The n move to in front. U power to the n minus 1. times u prime over second function square, because quotient rule. So from here, we simplify. First, we factorize, and then we simplify, and lastly, this is the answer. Look at the next example. Y equal to 3x minus 1 over x squared plus 3. So in first chapter, you know this is a rational function. So we can say this rational function has power 2. So we use the general power rule because the rational function has power 2. So n move to in front, u power to the n minus 1, 2 minus 1 is 1, then u prime. Our u now is rational function. So hope you understand, because u equal to gx is the inner function, and I let my inner function as 3x minus 1 over x squared plus 3. Then my outer function f x equal to x squared. So my f gx will equal to the 3x minus 1 over x squared plus 3 power 2. So that's why my u is rational function. So when we differentiate the rational function, we use quotient rule. So this is the quotient rule we have covered in previous section. So we differentiate the first function times second function minus we differentiate the second function times first function over second function square. This is a quotient rule. And then we simplify. So we can multiply these two fractions, and then we simplify. So this is the answer. Your answer must be in simplest form. Now look at this trigonometric functions and the chain rule. Differentiate the sign u with respect to x will equal to cosine u times u prime, where u is the inner function. Look at the first example, y equal to sine 2x. The general function is y equal to sine x, but now we have y equal to sine 2x. So why? I say this function is a composite function because look at the A. I can let my gx function or u equal to 2x. and my outer function fx equal to sine x. So my composite function fgx is sine 2x. So that is why sine 2x is a composite function. Here is a proof. And why we should use the chain rule to differentiate. So now we let u equal to 2x. Here is a proof. Let gx or u equal to 2x here, and we use chain rule. So y prime equal to cos u times u prime. Cos where u equal to 2x, so cos 2x times u prime. Differentiate the u with respect to x. So we have cos 2x times 2, so equal to 2 cos 2x. And same for b and c. The u is x minus 1, and the u for c is 3x. Here are the differentiation rules that we have covered. One of the most intriguing characteristics of the natural exponential function is that it is its own derivative. In other words, it is a solution to the differential equation y prime equal to y. This result is stated in the next theorem. Let u be a differentiable function of x. U is an inner function. So for the first one, differentiate the exponent x with respect to x equal to exponent x. And differentiate the exponent u with respect to x equal to exponent u times du dx. Look at this example. Find the derivative of each function. Y equal to exponent 2x minus 1. So this is a composite function. Because of, look at the A. I can let the inner function gx as 2x minus 1. And the outer function fx equal to exponent x. So my composite function fgx is equal to exponent 2x minus 1. So since this is a composite function, so we use second formula. Look at the solution. So let u equal to 2x minus 1. Here I show you the proof. The inner function is 2x minus 1. So for the second formula, exponent u times u prime. So we have exponent u, just rewrite back exponent 2x minus 1. Differentiate the 2x minus 1 with respect to x. We have 2. So that's why we have 2 here. For b, exponent negative 3 over x. So the inner function is negative 3 over x. Then we can change this form to power rule form. U will equal to negative 3 power to the minus 1. So we use constant multiple rule to get the u prime. So exponent u times u prime equal to, so here is exponent u times u prime. Use power rule. and we get this answer, and we simplify. The derivative of the natural logarithmic function, let u be a differentiable function of x, meaning that u is an inner function. Differentiate natural log of x with respect to x is equal to 1 over x. And differentiate the natural log of u with respect to x is equal to 1 over u times du dx, or equal to u prime over u. Look at this example. Differentiate the natural log of 2x with respect to x, where the u is 2x. So we use second formula, u prime over u. Differentiate the 2x, we will have 2 over u. Then simplify, we have 1 over x. For b, u equal to x squared plus 1. So same formula, u prime over u. So differentiate the x squared plus 1. Just use power rule because they are in the sum and different forms. We're able to differentiate. And over u. For c, differentiate x times natural log of x with respect to x. So look at this function. This function is in product form. So the main rule is product rule. The main rule is product rule. So we differentiate the second function times the first function plus differentiate the first function times second function. So in the first term here, for this part, differentiate natural log of x with respect to x. So we use the first formula on page 27, the first formula, because just only the natural log of x. It's not the composite function. So it's 1 over x. And differentiate the x with respect to x. So we use power rule. We have 1. So here we have 1 over x. And here we have 1. And then we simplify. Lastly, we have 1 plus natural log of x. For d, differentiate natural log of x cubed with respect to x. Be careful with this function. Natural log of x is a function of x. This function of x has power cube. So we use general power rule. So 3 move to in front. U is a natural log of x. U power to the n minus 1 times u prime. General power rule. You need to recognize the function. The function that has power, you need to use the general power rule. And differentiate the natural log of x with respect to x. So we use the first formula because this is not the composite function. So we have 1 over x here. So this is the answer. Because the natural logarithm is undefined for negative numbers, you will often encounter expression of the form natural log of modulus of u. The next theorem states that you can differentiate function of the form y equal to natural log of u, as though the absolute value notation was not present. if u is a differentiable function of x such that u not equal to 0, then differentiate natural log of u with respect to x equal to u prime over u. Find the derivative of fx equal to natural log of cosine x. This is the composite function. This is the composite function. Our u is cosine x. So we use the formula u prime over u. So to get the u prime, we differentiate the cos x with respect to x. So we have negative sine x. That you have learned how to differentiate the cosine x in fourth section. So over u is cosine x. Then we can convert the sine x over cosine x to be tangent x. To differentiate exponential and logarithmic functions to other bases, you have three options. Use the definition of a power to the x and log x base a, and differentiate using the rules for the natural exponential and logarithmic functions. Use logarithmic differentiation, or use the following differentiation rules for bases other than e given in the next theorem. Look at this theorem. Let a be a positive real number, a not equal to 1, and let u be a differential function of x. U is inner function. So we have differentiate the a power to the x with respect to x equal to natural log of a times a power to the x. And for the exponential function that has an inner function u, so we have natural log of a times a power to the u times u prime. For the third, differentiate the log x base a with respect to x equal to 1 over natural log of a times x. And for the log function that involve inner function, or we so-called the composite function, so we have 1 over natural log of a times u prime. Look at this example. Find the derivative of each function. Don't confuse the function. For a and b are exponential function that base other than e. Look at the example. The a, y equal to 2 power x. Y equal to 2 power to the x is an exponential function that bases other than e. The base now is 2. And don't confuse with x power 2. They are not same. This is a quadratic function. This is an exponential function, the base other than e. So, different formula. You differentiate a quadratic function, x squared, you use power rule. But you differentiate exponential function, the base other than e, you use the rule on page 33. look at the solution. For A, y prime equal to differentiate the 2 power to the x with respect to x. So this is the exponential function. The base other than e and is not in a composite function. So we use the first formula. Natural log of 2 times 2 power to the x. But for B, our function is 2 power to the 3x, where the 3x is inner function. So the function is composite function. So we use second formula on page 34. Second formula. So we have natural log of 2 times 2 power to the u times u prime. So this is the answer. For C, the function is log cosine x base 10. So it's composite function. So we use the fourth formula. So it's equal to negative sine x over natural log of 10 cosine x. And we simplify the sine x over the cos x. So we have tangent x. For D, our function is log radical x over x plus y, the base 3. So to solve this, to differentiate this function, we can rewrite the function using logarithmic properties. We call back the properties in chapter 2. For division, we can split it into the minus, two different log. So now, the first step, y can be written as log radical x over x plus y can be written as log radical x base 3 minus log x plus 5 base 3. And this radical x can be written as x power to the half. And we use the property, the power move to in front. So this also equivalent to log x power to the half base 3 minus log x power x plus 5 base 3. So this power, we use the property move to in front. So that's why we have this function. And after we rewrite our function in this form, so it's easier for us to differentiate because they are in different form. So we can straight away to differentiate the first term and also for the second term, rather than we use quotient rule. So we differentiate. We straight away to differentiate. So we differentiate the half log x base 3. So this one is a constant multiple rule. Half is a constant. So we just remain a constant and we just differentiate the log x base 3. So we use the first formula because this is not, we use the third formula because this is not the composite function. And for the second term, here, log x plus y base 3. This is a composite function. Inner function is x plus 5, so we use fourth formula. And then we simplify. So this is our final answer. And in simplest form. look at the power rule for real exponent. Let n be any number and let u be a differentiable function of x is a inner function. So differentiate the x power to the n with respect to x equal to n times x power to the n minus 1. For the second, differentiate the u power to the n with respect to x equal to n times u power to the n minus 1 times du dx. Look at this fifth example. Differentiate the exponent power to the exponent with respect to x. So this function actually is a constant. Exponent is a value. It's a 2.7. 2.7 power to the 2.7 is a constant. So the whole thing is a constant. And we differentiate the constant with respect to x is equal to 0. This is the constant rule. Differentiate the exponent x with respect to x. So we use exponential rule because this is an exponential function. For C, differentiate the x power to the exponent with respect to x. We use power rule because this one is polynomial function. X power to the cube, x power to the 2, x power to the exponent 2.7, x power to the 4 is a polynomial. So we use power rule. So for the power rule, n is the power, n move in front, times x n minus 1. The derivative of the transcendental function f(x) equal to natural log of x is the algebraic function f prime x equal to 1 over x. You will now see that the derivative of the inverse trigonometric functions also are algebraic. So look at this one. Let u be a differentiable function of x. So where the u is the inner function, differentiate arc sine u with respect to x. We have u prime over radical 1 minus u squared. And differentiate the arc cosine u with respect to x. We have negative u prime over radical 1 minus u squared. So note that the derivative of arc cosine u, arc cotangent u, and arc cosecant u, the right side, are the negative of the derivative of arc sine u, arc tangent u, and arc secant u at left side. The formula same, just the right side for these three functions have negative. Look at this example. Differentiate the arc sine 2x with respect to x, where the 2x is inner function, is u. The function is composite function. So use the formula u prime over radical 1 minus u squared. And we simplify. For B, differentiate the arctangent 3x with respect to x. This function also is composite function because the 3x is inner function. So we use the formula of arctangent. Then this is the answer. For C, differentiate the arc sine radical x with respect to x. Also is a composite function. So your first step, you can change the radical x to the power of half, x power to the half. So u prime over 1 minus u squared. So to get the u prime, we use power rule. Here is equivalent to x power to the half. So it's the u. Radical x can be written as x power to the half and equal to u. So we have formula is u prime. To get the u prime, we use power rule. Half move to in front, x power to the n minus 1 over radical 1 minus u squared. Our u is x power to the half, and then square. Half and 2 can be cancelled. So just power 1. So we simplify and we write our answer. For D, arcsecant exponent to x with respect to x. So we differentiate this function. So first, you should know this function is a composite function. This function is a composite function. So exponent to x is a u, is the inner function. So we use the formula, the arcsecant formula. So we have u prime over modulus of u times radical u squared minus 1. So how to get the u prime? This is a u, inner function. And how to get the u prime? So this function also is a composite function. This function also is a composite function. So involve chain rule. Now to get the u prime, we differentiate the u, the inner function of this function. So we will have exponent 2u times u prime 2. So we have 2 exponent 2u. This is a u prime. So that's why we have 2 exponent 2u here. And over modulus of u times radical u squared minus 1. And we simplify our answer. So the absolute value sign, the modulus sign here is not necessary because exponent to x is greater than 0.